On August 15th, 1977, a radio telescope in Ohio detected something unusual, a signal unlike any we had heard before, the most powerful ever recorded from deep space, and for 72 long seconds it whispered to us, steady, clear, using the very frequency you might choose if you wished to speak across the galaxy. The astronomer who found it was stunned, and on the printout he wrote only one word, wow. For 48 years, its origin remained a mystery, until yesterday, when Harvard astrophysicist Avi Loeb released new calculations suggesting something almost impossible. On that very day in August, an object sat 600 astronomical units away, pointed directly at Earth. And today, that same object is moving through our solar system at 60 kilometers each second. We call it 3I Atlas, larger than Manhattan, and the math tells us this is almost certainly not coincidence, with a 99.4% chance that Atlas was the source of that signal. Yet its behavior is strange. It emits pure nickel without iron, something seen only in industry. It carries lights that shine forward instead of a tail, and its path aligns perfectly with Mars, Venus, and Jupiter. In 29 days, on October 29th, it will slip behind the Sun, out of sight, unseen. Scientists argue, NASA insists it is only a comet, but the nickel remains unexplained, the trajectory unexplained, and the ancient signal still unexplained. The clock is moving. Soon Atlas will vanish into shadow, and if Avi Loeb is right, what comes after may change everything. This is the story they do not want you to hear, and if it speaks to you, stay with us as we drift deeper, and perhaps share in the comments where you are listening from, what time it is, and the strangest thing you have ever known. Chapter 1. The Signal from 3I Atlas. Breaking a 48-year mystery. Let me walk you through what Avi Loeb discovered. When you see the numbers, when you understand the geometry of what happened in 1977, you realize we are not dealing with cosmic coincidence. We are facing something that defies every probability model we have. On September 29, 2025, Loeb published his calculations. The timing matters, because 3I Atlas is approaching fast, and what he revealed connects two of the most mysterious events in astronomical history. The WOW signal and this interstellar visitor are not separate mysteries. They are the same mystery, separated by 48 years and hundreds of billions of kilometers. Here is what Jerry Eamon saw that night in August. The Big Ear radio telescope at Ohio State University was scanning the sky, listening for patterns in the cosmic noise. At 10:23 p.m. Eastern Time, the telescope locked onto something in the constellation Sagittarius. The signal strength jumped, not a little jump, a massive spike. The computer recorded it as 6EYY1KEH, a code meaning the signal was 30 times stronger than the background noise. Days later, Eamon reviewed the printout. When he saw those numbers, he grabbed a red pen, circled them, and next to the sequence he wrote, "Wow!" with an exclamation point. That margin note became the name the WOW signal, and for nearly 5 decades it remained unexplained. The signal lasted exactly 72 seconds. That is not random. It is the time it takes for Earth's rotation to sweep a fixed point in space through the Big Ear's field of view. Whatever transmitted that signal was not moving. It was sitting at a specific location in the sky, broadcasting at 1,420 megahertz, the frequency of neutral hydrogen, the most abundant element in the universe. If you wanted to send a signal any civilization would recognize as artificial, you would use that frequency. It is the cosmic calling card, but the signal never repeated. They pointed every available telescope back at that same spot in Sagittarius. Nothing. Silence. For 48 years, astronomers have been checking that location, and every time, nothing. It was as if something out there said hello once, and then went quiet forever. Until Avi Loeb did the math. Loeb is not a fringe figure. He is the Frank B. Baird Jr. Professor of Science at Harvard, former chair of the Astronomy Department, former chair of the Board on Physics and Astronomy of the National Academies. He has published over 900 papers. He is not some conspiracy theorist in a basement, he is establishment astronomy. Or at least he was, until he started asking questions that made his colleagues uncomfortable. The question he asked about 3I Atlas was simple. Where was this object in August 1977? 3I Atlas moves in a hyperbolic orbit, which means it is not bound to our Sunday. It came from interstellar space. It is passing through our solar system, and it will leave again, never to return. Because its orbit is hyperbolic, its position at any point in time, past or future, can be calculated with extraordinary precision. The math is clean. The gravitational equations do not lie. Loeb traced the orbit back to Earth. On August 15, 1977, 3I Atlas was approximately 600 astronomical units from Earth, 600 times the distance from Earth to the Sun, far out in the outer solar system, cruising beyond Neptune and Pluto, in that vast empty zone where sunlight is just another star. But distance is not the shocking part. The shocking part is direction. The WOW signal originated from sky coordinates of right ascension, 19 hours, 25 meters, 291 degrees, declination, 27 degrees. 3 days earlier, 3I Atlas was at right ascension, 19 hours, 40 meters, 295 degrees, declination, 19 degrees. That is a separation of roughly 4 degrees in right ascension and 8 degrees in declination. 4 degrees, 8 degrees. On the scale of the entire sky, that is nothing. The full sky is 360 degrees around and 180 degrees from pole to pole, and yet here the signal and the object were within less than 10 degrees. Loeb calculated the odds. Pick 2 random directions in the sky. What are the chances they will align within that margin? 0.6%, less than 1 chance in 160. Put another way, there is a 99.4% probability this is not a coincidence. Think about what that means. An interstellar object, traveling for millions or billions of years through the galaxy, happens to be within a few degrees of the exact spot where humanity detected its only confirmed candidate for an extraterrestrial signal, and it was there at the exact time the signal was sent. But Loeb did not stop there. He asked what kind of transmitter could produce the WOW signal from 600 astronomical units away. The detected intensity of the WOW signal was in the range of 54 to 212 Jansky, 2A, a unit of spectral flux density used in radio astronomy, and at that distance the source would need a power output of 0.5 gigawatt to 2 gigawatts. 2 gigawatts is the output of a large nuclear power plant, more than the Hoover Dam generates, and it was beaming at a very specific frequency, the hydrogen line, in a very specific direction toward Earth. Natural astrophysical sources do not do this. Pulsars emit across a broad range of frequencies. Quasars, the same. Magnetars, the same. Natural radio sources are messy, broadband, chaotic. The WOW signal was narrowband, coherent, targeted all the hallmarks of an artificial transmission. Now we know where it came from, or at least we know where something was when it was sent. The signal was also blue-shifted by about 10 kilometers per second. Blue shift means the source was moving toward us. The Doppler effect shifts light and radio waves toward shorter wavelengths when the source approaches. The WOW signal showed a blue shift consistent with an object approaching at 10 kilometers per second. 3I Atlas is approaching the Sun at about 60 kilometers per second. The blue shift is smaller than expected, but it is in the same ballpark. Loeb notes this in his paper. The velocities are not identical, but consistent enough not to rule out the connection. So here is what we are looking at. An object traveling through interstellar space for eons arrives in the outer solar system in the 1970 seconds and transmits a powerful narrowband signal at the hydrogen frequency aimed at Earth. Then it goes silent. For 48 years it cruises inward, deeper into the solar system, undetected because it is too far away and too faint, until July 1st, 2025, when the Atlas survey in Chile picks up a fast-moving object and realizes it is not orbiting the Sun, it is passing through, and when they trace its origin, it comes from Sagittarius, the same region of the sky where the WOW signal originated. Every time you add another layer, the coincidence becomes more improbable. Trajectory from the same region, timing, blue shift, power requirements consistent with an artificial source, the alignment. Each one taken alone you could dismiss, but together? This is where Loeb's critics have a problem, because you cannot explain this away with hand-waving. You cannot say, it is just a comet, and hope people stop asking questions. The math is public. The orbital data is public. Anyone can check these calculations, and when you do, you get the same answer. Either this is the most extraordinary coincidence in the history of astronomy, or 3I Atlas announced itself to us then, and we are only figuring it out now. But if it is not a coincidence, if this object really did send that signal, then we have to ask the next question: why? Why announce yourself and then go silent? Why broadcast once and never again? What is the purpose of a greeting you never follow up on? Unless the signal was not a greeting. Unless it was something else, a beacon, a warning, a test to see if anyone was listening. Or maybe the signal was never meant for us at all. Maybe we just happened to be in the way of a transmission aimed at something else, something closer, something already in our solar system. That thought should unsettle you deeply, because if 3I Atlas was communicating with something else, that means it is not alone. And if it is not alone, then the question shifts entirely. We stop asking whether we are being visited, and start asking how long they have been here watching, waiting, operating in the spaces between our awareness. Chapter 2: 5 Impossible Anomalies That Scream Artificial. We need to understand what 3I Atlas is doing right now, because its behavior is not normal. It is not acting like a comet. It is not acting like an asteroid. It is acting like something we have never seen before, and the closer we look, the stranger it gets. 5 anomalies. That is what Avi Loeb counts. 5 separate characteristics that, individually, are improbable. Combined, they are statistically impossible for a random natural object. When scientists talk about anomalies, they mean deviations from what we expect based on our models and observations. 1 anomaly, you investigate. 2 anomalies, you start asking questions. 5 anomalies, that is when you either rewrite the textbook or admit your model is missing something fundamental. Anomaly number 1, the trajectory. 3I Atlas is on a retrograde orbit, moving opposite to the direction the planets orbit the Sunday. Most objects in the solar system orbit in the same direction because they formed from the same rotating disk of gas and dust. Retrograde orbits are rare but not impossible. Comets from the Oort cloud can come in at any angle, so a retrograde orbit alone is not shocking. What is shocking is how precisely that retrograde orbit aligns with the ecliptic plane, the flat disk in which the planets orbit Earth, Mars, Venus, Jupiter, Saturn, all of them within a few degrees of the same plane, like a cosmic racetrack where everything stays in its lane. 3I Atlas is moving retrograde backward along that racetrack, but staying in the lane, with an orbital inclination of only about 5 degrees. For an object coming from interstellar space, that is absurdly well aligned. If interstellar objects arrive from random directions, you would expect them at any angle, because most of the sky is not aligned with the ecliptic. The probability that a random interstellar trajectory would align with the ecliptic plane to within 5 degrees is about 1 in 500 already. We are in the realm of the improbable. Anomaly number 2, the timing. 3I Atlas is not just aligned with the ecliptic, it is arriving at a time when it will pass close to multiple planets. Close, in astronomical terms, means within a few tens of millions of kilometers. On October 3rd, 2025, just days from now, 3I Atlas will pass within 29 million kilometers of Mars, close enough that cameras on spacecraft orbiting Mars will be able to image it in detail. But Mars is not the only near encounter. The trajectory also brings 3I Atlas close to Venus and Jupiter, not at the same time because the planets are spread out along their orbits, but its orbit is shaped such that it crosses near the orbits of all three planets. If you take the orbital path of 3I Atlas and randomize the time it enters the solar system, keeping the trajectory the same but changing when it arrives, the probability that it would pass as close as it does to Mars, Venus and Jupiter is about 1 in 20,000. Now we are stacking probabilities, 1 in 500 for the trajectory alignment, 1 in 20,000 for the timing. Multiply those together and you are approaching 1 in 10 million odds that this is random. But we are not done. Anomaly number 3, the disappearing act. 3I Atlas will reach perihelion, its closest approach to the Sun, on October 29th, 2025. Perihelion is normally the most interesting time for a comet because that is when it is most active, heated by the Sun, spewing gas and dust, putting on a show. For 3I Atlas, perihelion happens at about 1.4 astronomical units, just inside the orbit of Mars, close enough to get a good look, except we will not be able to see it, because on October 29th, 3I Atlas will be on the opposite side of the Sun from Earth. The Sun will be directly between us and the object. We will have no line of sight. For several weeks around perihelion, 3I Atlas will be hidden from every telescope on Earth and every spacecraft in the inner solar system. This is the perfect time to do something sneaky. If you were an interstellar spacecraft and wanted to change your trajectory without being observed, perihelion is when you would do it. A burn at perihelion, using the Sun's gravity to amplify your thrust in a maneuver called a solar oberth, is the most effective way to change your velocity. You get more change in speed for the same amount of fuel because you are deep in the Sun's gravity well when you fire your engines. If 3I Atlas maneuvers behind the Sun, we will not know until it re-emerges in December, and by then, if it has changed course, it could be heading anywhere. That timing feels deliberate. An object traveling for millions of years suddenly times its closest approach to coincide with the moment it is hidden from Earth. Maybe it is a coincidence, or maybe someone planned it that way. Anomaly number 4, the anti-tail. Comets have tails. The tail points away from the Sun because the solar wind and radiation pressure push gas and dust outward. This is basic cometary physics, observed for centuries. 3I Atlas does not have a normal tail, it has something else. On July 21st, 2025, the Hubble Space Telescope captured an image of 3I Atlas. The image shows a teardrop-shaped cocoon of dust surrounding the nucleus, but the cocoon is not symmetric. There is more material in front of the object facing the Sun than behind it. The dust is glowing ahead of the nucleus like headlights. This is backwards. Dust should trail behind. Radiation pressure should push it away from the Sun, creating a tail that streams back along the orbit. Instead, there is a glow in front, as if the object is illuminated from within, as if it is emitting something forward. Loeb suggests one explanation. If the nucleus does not spin, if it keeps the same face pointed toward the Sun at all times, then the day side would be perpetually hot and the night side perpetually cold. Ice on the day side would sublimate, turning directly from solid to gas, and that gas would carry dust particles with it, producing a forward glow instead of a trailing tail. But that explanation requires the nucleus to be tidally locked like the Moon is tidally locked to Earth. Tidal locking happens when an object orbits close to a much larger body for a long time. 3I Atlas is not orbiting anything. It is passing through. There has been no time for tidal locking. So why would it have stopped spinning? Unless it was designed that way, unless the object is maintaining a fixed orientation deliberately, keeping one side pointed toward the Sun because that side has something on it. Solar panels maybe, sensors, a transmitter. The glow itself is another puzzle. The Hubble image shows no prominent tail extending backward. For a comet that is already active at more than 4 astronomical units from the Sun, you would expect a significant dust trail by now, but it is not there, or at least it is much fainter than expected. The glow is concentrated around and in front of the nucleus, not streaming behind it. This does not fit the comet model. it fits something else. Anomaly number 5. The mass problem. On September 25, 2025, Avi Loeb published another paper with Richard Cloyt and Peter Veers, analyzing the trajectory of 3I Atlas in excruciating detail. Using data from 227 observatories worldwide and over 4,000 observations collected between May 15th and September 23rd, they were looking for non-gravitational acceleration. Non-gravitational acceleration is what happens when a comet jets gas. The gas escapes from the comet and, like a tiny rocket, pushes the comet slightly off the path it would follow under gravity alone. This is routine for comets. You measure the position over time, compare it to the predicted gravitational orbit, and the deviation tells you how much thrust the outgassing is producing. 3I Atlas is losing mass. The James Webb Space Telescope measured it at about 150 kilograms per second of gas venting into space, a fire hose of material pouring off the surface. With that much mass loss, you expect measurable non-gravitational acceleration. The jets should be pushing the nucleus around, causing small deviations in its orbit. Loeb and his colleagues found no deviation. 0. The orbit of 3I Atlas follows pure Newtonian gravity to within the measurement precision. Despite losing 150 kilograms per second, the object is not accelerating. That means one thing: it is too massive for the jets to move it. The thrust from the outgassing is negligible compared to the inertia of the nucleus. When you do the math, using the measured mass loss rate and the upper limit on acceleration, you get a minimum mass for 3I Atlas at least 33 billion tons. 33 billion tons is the mass of a mountain. For solid density rock or ice, that implies a diameter of at least 5 kilometers. If 3I Atlas is a solid object 5 kilometers across, it is enormous, much bigger than the previous interstellar visitors. 1I, Oumuamua, the first interstellar object discovered in 2017, was estimated to be a few hundred meters long. 2I divided by Borisov, the interstellar comet discovered in 2019, had a nucleus maybe half a kilometer across. 3I Atlas is an order of magnitude larger, 10 times the diameter, 1,000 times the volume, 1,000 times the mass. But here is the statistical problem. Small objects are much more common than large objects. In the asteroid belt, in the Kuiper belt, in interstellar space, the size distribution follows a power law. For every big rock, there are thousands of smaller rocks. We have detected 3 interstellar objects. 2 are small. Now, suddenly, the third one is 5 kilometers or more. That is backwards. We should have found hundreds or thousands of smaller interstellar objects before we found one this big. The probability of detecting a 5-kilometer object in a sample size of 3 is astronomically low. Unless 3I Atlas is not a random rock, unless its size is not a coincidence, unless it is large because it was designed to be large because it needs to carry something, because it has a purpose that requires mass and structure. Stack all 5 anomalies together: the ecliptic alignment 1 in 500, the planetary encounter timing 1 in 20,000, the perihelion timing that hides it from observation at the critical moment, the forward glow that defies cometary physics, the anomalous mass that defies statistical expectations. Each one alone is improbable. Together, they form a pattern. And patterns are what we look for when we search for intelligence. Think about crossing a street. If there is a 40% chance that a car will hit you, you watch that car. You do not assume everything is fine. You pay attention. That is where we are with 3I Atlas. The anomalies are piling up, the probabilities are stacking against natural explanations, and we are about to get our closest look yet. In just days, cameras on Mars will capture images with resolution 100 times better than anything we have seen. We will finally see the nucleus separated from the dust cloud. We will know if it is 5 kilometers across, or something else entirely. And that knowledge might change everything we thought we understood about what is possible. Chapter 3. The chemical signature of technology. When you study a comet, You learn what it is made of by analyzing the light it emits and reflects spectroscopy. You spread the light into a spectrum like a rainbow and look for dark absorption lines or bright emission lines at specific wavelengths. Each chemical element and molecule has a unique fingerprint. Sodium glows yellow, hydrogen emits red, water shows specific infrared bands. By measuring which wavelengths are present and which are missing, you can deduce the composition. Comets are made of ice and rock, mostly water ice with some carbon dioxide, carbon monoxide, methane, ammonia, and dust grains made of silicates and organic compounds. When a comet approaches the sun and heats up, those ices sublimate, turning directly from solid to gas without melting. The gas escapes, carrying dust with it, forming the coma and tail. By analyzing the spectrum of that gas and dust, we learn what the comet is made of. 3I Atlas has been observed by multiple telescopes since its discovery. Hubble imaged it in visible light. Webb observed it in infrared. The Very Large Telescope in Chile captured spectra showing emission lines from specific molecules. NASA's SphereX Space Telescope measured its brightness at multiple infrared wavelengths. Each observation added another piece to the puzzle, and the puzzle does not fit. Start with the gas composition. The James Webb Space Telescope observed 3I Atlas on the 6th of August 2025. Using its near-infrared spectrograph, Webb is extraordinarily sensitive. It can detect faint molecular signatures that other telescopes miss. The spectrum revealed carbon dioxide, water, carbon monoxide, and carbonyl sulfide. Those are all expected in comets, but the ratios were wrong. 95% carbon dioxide, 5% water, with trace amounts of carbon monoxide and carbonyl sulfide. That is the opposite of what you find in solar system comets, which are typically water-rich. Water is the most abundant volatile in comets, because water ice is common in the cold outer regions of planetary systems where comets form. Carbon dioxide is present, but usually as a minor component. A typical comet might be 80% water, 10% carbon dioxide, 10% other stuff. 3I Atlas is 95% carbon dioxide and only 5% water. That is inverted, backwards. Like finding a human whose body is 95% bone and 5% water, it is chemically bizarre. Stephanie Millam, an astrochemist at NASA Goddard Space Flight Center who worked on the Webb observations, suggested that the surface of 3I Atlas might have been altered by cosmic rays during its long journey through interstellar space. Cosmic rays are high-energy particles, mostly protons, that zip through the galaxy at nearly the speed of light. When they hit ice, they can break chemical bonds and create new molecules. Over millions or billions of years, that radiation could cook the surface, converting some of the water ice into carbon dioxide and other compounds. Millam called it a cooked shell. That is a reasonable hypothesis, but it has problems. First, cosmic ray bombardment affects the surface, not the interior. When the comet starts outgassing, you would expect the surface layer to blow off quickly, exposing fresh interior ice that has not been cooked. The spectrum should evolve over time, starting carbon dioxide rich and transitioning to water rich as the surface ablates. But 3I Atlas has been active for months, and the spectrum is still carbon dioxide dominated. If anything, the carbon dioxide production is increasing as it gets closer to the Sunday. Second, other interstellar objects have not shown this. 2I divided by Borisov, the previous interstellar comet, had a composition similar to solar system comets, water-rich, with normal ratios of other volatiles. If cosmic ray cooking is a universal process for interstellar objects, why does Borisov look normal and 3I Atlas look weird? Third, the magnitude of the effect. 95% carbon dioxide is extreme. To convert that much water ice into carbon dioxide requires intense radiation over a long time, and even then, you would expect a mix of products, not just carbon dioxide. The chemistry does not quite add up. So maybe the surface was cooked by cosmic rays, Or maybe 3I Atlas formed in a planetary system where carbon dioxide ice was more abundant than water ice. That could happen in certain temperature zones of a protoplanetary disk. But it is unusual. Water is common because oxygen is common, and hydrogen is the most abundant element. To get a carbon dioxide-rich comet, you need special conditions. Not impossible, but not common either. Or maybe the carbon dioxide is not outgassing from ice. Maybe it is being produced by some other process. Chemical reactions, decomposition of organic material, or something artificial. Propellant, perhaps. Carbon dioxide is used as a propellant in spacecraft thrusters. It is stable, easy to store, and provides decent thrust. If 3I Atlas were a spacecraft, venting carbon dioxide would be a way to maneuver without producing a bright, obvious rocket exhaust. That is speculative, not a claim, but the carbon dioxide dominance is anomalous, and the explanations we have are not fully satisfying. Keep that in your back pocket as we add more anomalies. Now, let us talk about the nickel. On the 25th of August 2025, the Very Large Telescope in Chile observed 3I Atlas using its UVS spectrograph. UVS stands for Ultraviolet and Visual to Shell Spectrograph, a high-resolution instrument that can resolve fine details in the spectrum. The team, led by Rohan Rahat Gaunkar and Thomas Puzia, detected emission lines from nickel atoms in the coma, 22 distinct spectral lines, all consistent with neutral nickel, fluorescing under solar ultraviolet light. The nickel was definitely there. Nickel in comets is not shocking. Comets contain dust grains made of rocky and metallic material. When those grains are heated, either by sunlight or by collisions in the coma, they can release atoms of various elements. Nickel is one of them. It has been detected in other comets. Sodium, iron, magnesium, calcium, nickel, all show up in cometary spectra when you look carefully. What is shocking is that the Very Large Telescope detected nickel but no iron. Iron is usually detected alongside nickel because they are chemically similar and form together in stellar nucleosynthesis. When a massive star explodes in a supernova, the explosion creates both nickel and iron in roughly similar amounts. The solar system, and presumably other planetary systems, inherit that ratio. Rocky material, whether in planets, asteroids, or comets, contains both nickel and iron. Every comet ever studied in detail shows iron and nickel together. Sometimes iron is more prominent, sometimes nickel, but both are present. The ratio varies, but the pairing is universal. Nickel without iron is unheard of in natural space objects except in 3I Atlas. The VLT spectrum shows strong nickel emission and no detectable iron emission. The iron lines that should be there are absent. The team checked carefully. They looked for iron lines at multiple wavelengths. Nothing. The upper limits are tight enough that if iron were present at the same abundance as nickel, it would have been detected. It is not there. Thomas Puzia, one of the lead astronomers, said this opens a door to a whole new world of chemistry that we never had access to before. He is right. But the question is whether that chemistry is natural or artificial. On Earth, nickel without iron is produced industrially. Nickel refining separates nickel from iron ore using chemical processes. The Mond process, for example, uses nickel carbonyl, a gaseous compound, to extract pure nickel. Nickel carbonyl forms when carbon monoxide reacts with nickel at moderate temperatures. The gas is then decomposed at higher temperatures, depositing pure nickel metal. It is a standard industrial technique. Nickel alloys used in aerospace and engineering are often high-purity nickel with minimal iron. Stainless steel jet engine components, spacecraft structural materials all use refined nickel. When you see nickel without iron, the first thought is industrial processing. Avi Loeb made this point explicitly. Nickel without iron is a signature of industrial production of nickel alloys. It is what you would expect from technology, not from a natural rock. And 3I Atlas is shedding this stuff at an increasing rate. When first detected in July, At about 3.9 astronomical units from the Sun, the nickel emission was faint. By late August, at about 2.8 astronomical units, the production rate had increased 25-fold, 25 times more nickel in just 1 month. The closer it gets to the Sun, the more nickel it produces. The rate of increase is also anomalous. The VLT team fit the data to a power law. The nickel production rate goes as the inverse heliocentric distance raised to the power of about 9, distance to the power of -9. That is an extremely steep dependence. For comparison, typical cometary activity scales as distance to the power of -2 or -3. An exponent of -9 means the activity is ramping up much faster than normal as 3I Atlas approaches the Sunday. Why would nickel production increase so dramatically? One possibility is that the surface is layered, maybe the outer layer is nickel-rich and iron-poor, and as that layer sublimates, it exposes more of the same material underneath, causing the emission to grow. But that requires explaining why the surface is nickel-rich in the first place, and it does not explain the lack of iron. Another possibility, suggested by the VLT team, is nickel carbonyl. If the surface contains nickel carbonyl molecules, those molecules are extremely volatile. They sublimate at very low temperatures, much lower than water ice. Nickel carbonyl could be outgassing even when the comet is far from the Sun, and as the temperature rises, the production rate increases rapidly. When nickel carbonyl breaks apart, it releases nickel atoms, which fluoresce in sunlight, producing the observed emission lines. Nickel carbonyl is a real molecule. It exists. It is used in industrial nickel refining. The question is whether it exists naturally in comets. We have never detected it before, not in solar system comets, not in interstellar space. It is chemically plausible, but observationally unprecedented. And here is the thing. If nickel carbonyl is present in 3I Atlas, where did it come from? Carbonyl compounds form when carbon monoxide reacts with metals. That reaction typically requires specific conditions, temperatures, and pressures that might not be common in the cold environment of a forming planetary system. Or maybe they are common, and we just have not looked carefully enough. Then there is the color change. In early September, astronomers Michael Yeager and Gerald Raymond captured images showing 3I Atlas had shifted from a reddish hue to a vivid green glow. Green in comets usually comes from diatomic carbon molecules or cyanogen. The Very Large Telescope detected a steep rise in cyanide production around the same time. Cyanide production increasing alongside nickel production, both ramping up at extreme rates as the object approaches the Sun, both showing chemical signatures that are unusual or unprecedented. The pattern keeps building. Each new observation adds another piece that does not quite fit the natural comet model, or fits it so poorly that you have to invoke special circumstances, exotic chemistry, rare conditions, things we have never seen before. At some point you have to ask whether we are stacking too many special cases, whether the simplest explanation is not that this is an extremely weird comet with extremely unusual chemistry, but rather that it is something else entirely, something that was never a comet to begin with. Chapter 4. The Loeb Scale. How dangerous is it? When Avi Loeb started talking about 3I Atlas as potentially technological, he knew he needed a framework, a way to communicate the level of concern without either crying wolf or ignoring a genuine threat. So he developed what is now called the Loeb Scale, a ranking system from 0 to 10 that measures the likelihood and potential danger of interstellar objects being artificial. 0 on the scale means definitely natural, an object that exhibits properties consistent with known classes of comets or asteroids. 2I divided by Borisov, the previous interstellar comet, would rank as 0. It looked like a comet, acted like a comet, had the chemistry of a comet, no anomalies, no mysteries, just an icy rock from another star system passing through. 10 on the scale means confirmed artificial object on a collision course with Earth, carrying global catastrophic consequences, an existential threat, the kind of scenario where humanity would need to respond immediately with every resource available, though the response might prove futile. Between 0 and 10, The scale gradates through increasing levels of anomaly and threat. Level 1 captures objects with minor deviations or inconclusive data. Level 2 describes unusual properties that still fall within the range of natural phenomena. Level 3 marks persistent anomalies, features that challenge our models but do not yet demand a technological explanation. Level 4 is where 3I Atlas sits right now, according to Loeb. Level 4 means multiple anomalies that are difficult to explain naturally, a pattern emerging that suggests possible artificial origin, but not yet confirmed, 40% probability that this is technology, 60% probability that it is natural but extremely unusual. Think about that for a moment. 40%. If you were crossing a street and someone told you there is a 40% chance a car will hit you, you would not cross. You would wait. You would watch. You would take the threat seriously, even though it is more likely than not that you will be fine. Level 5 would be reached if additional evidence tips the balance past 50% more anomalies, stronger signatures, behaviors that cannot be explained by any known natural process. Level 6 means the object is very likely artificial based on multiple independent lines of evidence, though not yet proven beyond reasonable doubt. Level 7 is where you start talking about confirmed technology. The object has maneuvered in ways that require propulsion. It has transmitted signals. It has displayed geometries or behaviors that are unambiguously artificial. At level 7, the debate is over. We know it is technology. The question becomes what kind, and what does it want? Level 8 means confirmed artificial object that poses no immediate danger. A flyby, perhaps. A probe observing us from a safe distance. Still a monumental discovery. Still world-changing, but not an immediate threat to human survival. Level 9 is when the confirmed artificial object is on a trajectory that could cause regional harm, an impact equivalent to a major nuclear strike, something that could devastate a city or a country but not end civilization. Level 10, as mentioned, is the highest designation confirmed artificial body on a collision course with Earth, carrying global consequences. The asteroid that killed the dinosaurs was about 10 kilometers across. 3I Atlas might be 5 kilometers or more. If it were on a collision course at 60 kilometers per second, the impact would release energy equivalent to millions of nuclear weapons. The resulting dust cloud would block sunlight for years. Global temperatures would plummet. Agriculture would collapse. It would be an extinction-level event. But 3I Atlas is not on a collision course with Earth. Its trajectory will keep it at least 1.8 astronomical units away from us, about 270 million kilometers farther than the distance from Earth to the Sunday. So, even if it is artificial, even if it has hostile intent, it is not currently aimed at us. However, trajectories can change. That is why the perihelion maneuver matters so much. If 3I Atlas executes a burn behind the Sun in late October, it could alter its path. Loeb and his colleagues calculated the velocity change needed to reach Earth. A delta V of 30 to 40 kilometers per second during October could bring the object, or components of it, to Earth between late December 2025 and early January 2026. 30 to 40 kilometers per second is a lot more than current human spacecraft can achieve with chemical rockets, but it is not impossible. Ion drives, nuclear thermal propulsion, or more exotic systems could do it. And if 3I Atlas has been traveling for millions of years, it presumably has some kind of propulsion system that allowed it to navigate across interstellar distances. The timing window matters. If something arrives at Earth in late December or early January, we would have very little warning, maybe a few weeks at most, depending on how reflective the object is and whether our telescopes happen to be pointed in the right direction. That is not enough time to mount any kind of defense. We do not have the infrastructure to intercept a 5-kilometer object moving at interstellar speeds. We barely have the capability to deflect small asteroids moving much slower. So level 4 on the Loeb scale is not nothing. It is a yellow alert, a recognition that we are dealing with something anomalous, something that demands attention and observation, something that could escalate if the anomalies continue to accumulate. Now, let me talk about the dark forest hypothesis, because it is relevant to how we think about potential threats from interstellar visitors. The dark forest hypothesis is a proposed solution to the Fermi paradox, the question of why we have not detected any signs of alien civilizations, despite the vast number of stars and planets in the galaxy. The hypothesis, popularized by science fiction author Liu Cixin in his novel The Dark Forest, goes like this. The universe is like a dark forest. Every civilization is a hunter moving through the trees, trying to survive. The forest is full of other hunters, but you cannot see them and you do not know their intentions. If you reveal your location by making noise, you risk being targeted by a hunter who perceives you as a threat. The logic is brutal but simple. Resources are finite. Any civilization that expands will eventually compete for resources. If you encounter another civilization, you have two choices: cooperate or eliminate the potential threat. But cooperation requires trust, and trust requires communication, and communication takes time. Light speed limits mean that by the time you send a message and receive a response, decades or centuries might pass. Meanwhile, the other civilization could be developing weapons or expanding toward your territory. So the safest strategy under these assumptions is to strike first. If you detect another civilization, you eliminate it before it can become a threat to you. This creates a selection effect. Civilizations that reveal themselves get destroyed. Civilizations that stay quiet survive. Over time, the galaxy becomes filled with silent, paranoid civilizations, each hiding in the dark forest, afraid to make a sound. It is a grim scenario. It suggests that first contact might not be a friendly exchange of knowledge and culture. It might be a preemptive strike by a civilization that sees us as a potential threat and decides to neutralize us before we become dangerous. Is the dark forest hypothesis true? We do not know. It is speculation based on game theory and assumptions about how advanced civilizations might behave. But it is not implausible. History shows that when technologically advanced civilizations encounter less advanced ones, the results are often catastrophic for the less advanced. Colonialism, conquest, exploitation, the pattern repeats. If 3I Atlas is a probe from an advanced civilization, what are its intentions? Is it here to observe, to communicate, to assess whether we are a threat, or is it here to do something more sinister? Loeb mentions the possibility that 3I Atlas could be a mothership, a large carrier that releases smaller probes as it passes through the solar system. The smaller probes could be sent to investigate planets, moons, or other objects of interest. They could be reconnaissance drones. They could be weapons. We would not know until they deploy. The trajectory of 3I Atlas makes this plausible. Passing close to Mars, Venus, and Jupiter means that small probes ejected from the main object could reach those planets with minimal thrust. A probe ejected toward Mars when 3I Atlas is at closest approach would only need a few kilometers per second of delta V to intercept, achievable with simple chemical propulsion. Earth is trickier because 3I Atlas never comes very close to us, but if it maneuvers at perihelion, it could adjust its trajectory to release probes that reach Earth. Or it could already have released probes months ago, and we would not know, because we cannot detect objects smaller than about 100 meters at interstellar distances. This is why Loeb is advocating for increased monitoring. The Galileo project, which he leads, operates observatories that scan the sky for unidentified anomalous phenomena. If 3I Atlas does release probes, and if those probes enter Earth's atmosphere or begin maneuvering in near-Earth space, the Galileo project instruments should be able to detect them. The project currently has 3 observatories, one in Massachusetts, one in Pennsylvania, and one in Nevada. They use a combination of optical and infrared cameras, as well as algorithms to identify and track objects that do not follow normal flight patterns. Aircraft, satellites, meteors all have predictable trajectories and signatures. An alien probe would stand out. It would maneuver in ways that defy aerodynamics. It would emit or reflect light in unusual ways. It would be detectable, assuming we are looking. But detection is only the first step. If we detect alien probes, then what? Do we attempt communication? Do we try to capture one? Do we treat it as a threat and attempt to destroy it? These are questions that governments and militaries should be thinking about, but as far as anyone can tell, there are no established protocols for dealing with alien technology in near-Earth space. The October 29 perihelion passage is the critical moment that is when 3I Atlas will be most active, heated by the sun, and hidden from view behind the solar disk. If it is going to do something, that is when it will do it, and we will not know until it re-emerges in December. By then, if probes have been deployed, they could already be on their way to Earth or other targets. The time to prepare is now, not after the fact. Chapter 5, October 3rd, The Mars Encounter. This week right now, as you listen to this, 3I Atlas is approaching Mars. Within days, possibly within hours depending on when you are hearing this, the object will pass within 29 million kilometers of the red planet. That might sound far, but in astronomical terms, it is incredibly close, close enough that spacecraft orbiting Mars will be able to capture images with unprecedented detail. The HiRISE camera aboard NASA's Mars Reconnaissance Orbiter is the key instrument. HiRISE stands for High Resolution Imaging Science Experiment. It is one of the most powerful cameras ever sent to another planet. Designed to scout landing sites for Mars rovers, it can resolve features as small as 1 meter across on the Martian surface from orbit. But on October 3rd, HiRISE will not be pointed at Mars, it will be pointed at 3I Atlas. And from a distance of 29 million kilometers, it will achieve a pixel resolution of about 30 kilometers. That means each pixel in the image will represent roughly 30 kilometers of the object's surface. 30 kilometers per pixel does not sound impressive compared to the close-up images we get of Mars, where individual boulders are visible. But for an interstellar object moving at 60 kilometers per second, this is revolutionary. No spacecraft has ever gotten this close to an interstellar visitor. When Oumuamua passed through in 2017, we only detected it after it had already made its closest approach to the Sun and was on its way out. We got blurry images from ground-based telescopes, not enough to resolve any surface features. 2I divided by Borisov was observed in more detail, but again, only from Earth-based telescopes. The resolution was limited. 3I Atlas is different. We have spacecraft positioned near Mars, and 3I Atlas is passing right by them. For the first time, we will get a resolved image of an interstellar object. We will be able to separate the nucleus from the surrounding dust cloud. We will see the shape, the surface features, the brightness distribution. If there are large-scale structures on the surface, if the object is not a simple, irregular lump of rock and ice, HiRISE should be able to detect it. What are we looking for? Several things. First, the size. The current estimates for the nucleus of 3I Atlas range from about 0.5 kilometer to 5.5 kilometers in diameter. That is a huge uncertainty. HiRISE will narrow that down by measuring how much sunlight the brightest pixels reflect, and by assuming a reasonable value for the surface reflectivity, called albedo, astronomers can calculate the surface area of the nucleus. From the surface area and an assumed shape, they can estimate the diameter. If the nucleus turns out to be at the larger end of that range, 5 kilometers or more, then the mass problem becomes acute. As mentioned earlier, finding such a large interstellar object so early in our search is statistically implausible. It would strengthen the argument that 3I Atlas is not a random rock, but something deliberately constructed. Second, the shape. Natural comets and asteroids tend to be irregular, potato-shaped, with cratered surfaces and rough terrain. They are rubble piles, collections of smaller fragments held together by gravity, or monolithic chunks of rock and ice that have been battered by impacts over billions of years. If 3I Atlas has a highly regular shape, if it is spherical or cylindrical, or has flat surfaces and sharp edges, that would be a red flag. Artificial objects have geometries that natural objects do not. Think about Oumuamua. It was described as elongated, with a length-to-width ratio of about 10:1, like a cigar or a pancake, depending on which interpretation you believed. Some researchers suggested it could be a fragment of a planet torn apart by tidal forces. Others suggested it could be a light sail, a thin reflective sheet used for propulsion by reflecting sunlight. The debate was never resolved because the images were too blurry. We could not see enough detail to distinguish between the possibilities. With 3I Atlas, we might finally get that detail. If high-rise images show a regular geometry, if the object has symmetry that natural processes do not produce, it will be impossible to ignore. Third, the dust cloud. High-rise should be able to see how the dust is distributed around the nucleus. Is it symmetric? Is it concentrated in certain directions? Does it show jets or plumes emanating from specific locations on the surface? Comets often have active regions, spots where subsurface ice is exposed and outgassing occurs. Those jets can be highly directional, producing plumes that look like geysers. If the dust cloud around 3I Atlas shows unusual structure, if there are plumes pointing in directions that do not make sense for natural outgassing, that would be another anomaly to add to the list. For example, if there are jets pointing sideways or backwards relative to the sun, that would suggest active maneuvering rather than passive sublimation. Fourth, precursor objects. This is speculative but important. If 3I Atlas has released smaller probes, and if those probes are ahead of the main object on trajectories toward Mars, HiRISE might be able to detect them. Ground-based telescopes cannot resolve objects smaller than about 100 meters at the distance of Mars, but HiRISE, from its vantage point in Mars orbit, can detect much smaller objects if they are close enough and reflective enough. Avi Loeb calculated that if 3I Atlas released a probe that traveled about 30 million kilometers ahead and sideways toward Mars, that probe could intercept Mars around the same time as the main object's closest approach. A probe moving at just a few kilometers per second relative to 3I Atlas could cover that distance in the weeks or months since the object became active. Would HiRISE see such a probe? Maybe. It depends on the size and reflectivity of the probe and whether it happens to be in HiRISE's field of view at the right time. But if there is a probe, and if we detect it, that changes everything. That confirms technology. That moves 3I Atlas immediately to a much higher ranking on the Loeb scale. ESA's Mars Express and ExoMars Trace Gas Orbiter are also observing 3I Atlas during the encounter. Mars Express carries the high-resolution stereo camera and several spectrometers. ExoMars has the color and stereo surface imaging system and the Nomad spectrometer. These instruments will attempt to measure the spectrum of light from 3I Atlas, looking for specific molecular signatures in the coma. The spectrometers can detect molecules like water, carbon dioxide, carbon monoxide, methane, ammonia, and various organic compounds. By comparing the spectrum observed from Mars orbit with the spectra observed from Earth-based telescopes and from Webb, astronomers can build a more complete picture of the chemical composition. If there are molecules present that were not detected before, or if the ratios of molecules change as the object gets closer to the Sun, that information is valuable. ESA cautioned that 3I Atlas will be relatively faint and far away, so the images from Mars Express and ExoMars might not be spectacular. The object will cover less than a pixel in their cameras, so we should not expect detailed surface images. But the spectrometers might still pick up useful data, especially if the coma is bright enough. The observations are scheduled for October 1st through October 7th, with the closest approach on October 3rd. By the time you hear this, the observations may have already happened. The data will be downlinked from the spacecraft to Earth, processed and analyzed. It will take days or weeks for the results to be published. But when they are, we will know more about 3I Atlas than we do now. We will have hard data to either support or refute the anomalies. If the HiRISE image shows a 5-kilometer nucleus with irregular shape and normal dust distribution, and if the spectra show typical cometary composition, then the technological hypothesis takes a hit. It does not disappear because the trajectory and mass anomalies remain, but it becomes harder to argue that this is artificial if it looks and acts like a comet up close. On the other hand, if the high-rise image shows something unexpected, if the shape is too regular, if there are structures that should not be there, if the dust distribution is weird, if there is any sign of precursor probes, then the technological hypothesis strengthens. We move up the Loeb scale. The conversation shifts from speculation to serious consideration of what to expect. And there is another spacecraft that could observe 3I Atlas, though it is further away and the decision has not been made. NASA's Juno spacecraft is currently orbiting Jupiter. Juno's primary mission is to study Jupiter's atmosphere, magnetic field, and interior structure. But its mission is nearing its planned end. The spacecraft has far exceeded its original timeline and is running low on fuel. In March 2026, 3I Atlas will pass relatively close to Jupiter, about 25 million kilometers away. That is not as close as the Mars encounter, but it is still close enough for Juno's instruments to observe the object. Juno carries cameras, spectrometers, and a particle detector. It could analyze the composition of the coma in more detail, measuring isotopic ratios and trace elements that are difficult to detect from Earth. Avi Loeb and others have advocated for redirecting Juno to intercept 3I Atlas. It would require a trajectory change, a burn of Juno's engines to put it on a path that brings it closer to the object. The maneuver would need to happen soon, in mid-September or early October, to set up the March encounter. After the encounter, Juno would not have enough fuel to return to Jupiter orbit. The spacecraft would be sacrificed for this one observation. NASA has not committed to the maneuver. The decision involves trade-offs. Juno is still collecting valuable data about Jupiter. Ending the mission early to chase an interstellar object is a gamble. If 3I Atlas turns out to be a boring comet, the scientific community would question whether it was worth sacrificing Juno. But if 3I Atlas is something extraordinary, the data from a close encounter could be priceless. The Mars observations happening right now will likely influence NASA's decision. If the October 3rd data shows significant anomalies, the case for redirecting Juno becomes much stronger. If the data shows nothing unusual, NASA will probably keep Juno focused on Jupiter. Either way, we are about to learn a lot more about what we are dealing with. Chapter 6. October 29th. The disappearing act behind the sun. October 29th, 2025 mark that date. That is when 3I Atlas reaches perihelion, its closest approach to the Sunday. For any comet, perihelion is the most dramatic moment. The sun's heat intensifies, ice sublimates at maximum rate, the coma brightens, the tail extends. It is when comets put on their best show, when they are most visible, most active, most interesting to observe. But we will not see it. On October 29th, 3A Atlas will be on the opposite side of the Sun from Earth. The geometry of the orbits places the Sun directly between us and the object. For several weeks before and after perihelion, 3I Atlas will be lost in the solar glare, invisible to every telescope on Earth and every spacecraft in the inner solar system. This is not unusual. Comets often pass behind the Sun from our perspective. It is frustrating for astronomers because they miss the peak activity, but it happens. The orbital mechanics do not care about our viewing convenience. Objects go where gravity takes them. Except with 3I Atlas, the timing feels deliberate. An object that has traveled for millions or billions of years. An object with a trajectory that aligns with the ecliptic plane to within 5 degrees. An object that passes close to Mars and Venus and Jupiter at just the right times, also happens to reach its closest approach to the Sun when it is perfectly hidden from Earth's view. One more coincidence stacked on top of all the others. If you were designing a spacecraft and you wanted to do something without being observed, perihelion behind the Sun is exactly when you would do it. Let me explain why. A solar Oberth maneuver is one of the most efficient ways to change velocity in space. The principle is simple. When you are deep in a gravity well moving fast, a small thrust from your engines produces a larger change in your final velocity than the same thrust would in deep space. It is like pushing on a swing at the bottom of its arc versus pushing at the top. The timing matters. At perihelion, 3I Atlas will be about 1.4 astronomical units from the Sun, roughly 210 million kilometers. It will be moving at its maximum speed relative to the Sun, around 90 kilometers per second at closest approach. If it fires engines at that moment, even a modest thrust amplified by orbital mechanics can produce a significant trajectory change. How much thrust would be needed to reach Earth? Loeb calculated this. A velocity change of 30 to 40 kilometers per second applied at perihelion could put 3I Atlas, or fragments ejected from it, on a trajectory that intersects Earth's orbit. The arrival window would be late December 2025 to early January 2026. 30 to 40 kilometers per second is a lot of delta V. Current human spacecraft using chemical rockets cannot achieve that. The fastest spacecraft we have ever built, the Parker Solar Probe, reaches speeds of about 190 kilometers per second relative to the Sun, but that is after multiple gravity assists from Venus and years of acceleration. It does not have 30 kilometers per second of delta V available for maneuvering. But 3I Atlas is not a human spacecraft. If it is artificial, it has been traveling through interstellar space for a very long time. It presumably has propulsion systems beyond our current technology, ion drives, nuclear engines, advanced propulsion, something that can generate sustained thrust over long periods or deliver high impulse burns when needed. Would we detect such a maneuver? Maybe not. If the thrust is applied when the object is behind the Sun, we cannot see the exhaust plume. We cannot see the trajectory change in real time. We will only know if it maneuvered when it re-emerges in December and we recalculate its orbit. If the new orbit differs from the predicted orbit, if the object is not where it should be, based on pure gravitational mechanics, then it maneuvered. The problem is that by the time we detect a maneuver, it will be too late to respond. If 3I Atlas or something it releases is heading toward Earth, and we only find out in December, we have weeks at most to prepare. There is no planetary defense system capable of intercepting a 5-kilometer object moving at interstellar speeds with only a few weeks of warning. Even detecting it would be challenging. 3I Atlas is faint. It only became visible to our telescopes once it got close enough and active enough to reflect significant sunlight. If it releases smaller probes, objects tens or hundreds of meters across, they would be much harder to detect. We might not see them until they are very close, possibly not until they enter the inner solar system, or even Earth's atmosphere. This is why Loeb emphasizes the need for monitoring. The Galileo Project observatories should be watching the sky in late December and early January, looking for anomalous objects. If something arrives, if there are probes or fragments on approach, detection is the first step toward any kind of response. But what would the response be? That is the uncomfortable question nobody wants to answer. There are no established protocols for dealing with potentially hostile alien technology approaching Earth. We have protocols for asteroid impacts. We have early warning systems, impact prediction models, and theoretical deflection strategies. But those are for natural objects following predictable orbits, objects we can track for years before they pose a threat. An alien spacecraft, or probes released from one, would not follow those rules. They could maneuver unpredictably. They could accelerate or decelerate. They could change course mid-flight. All of our asteroid deflection strategies assume the target is passive, that it will not fight back or evade. An intelligent adversary changes everything. And there is another scenario to consider. What if 3I Atlas does not maneuver toward Earth? What if it maneuvers toward Jupiter instead? The trajectory of 3I Atlas takes it relatively close to Jupiter after perihelion. A smaller velocity change, 10 to 15 kilometers per second, could put it on a course that brings it much closer to Jupiter than currently predicted. Close enough for detailed observation of the gas giant and its moons, close enough to deploy probes into Jupiter's atmosphere, or onto the surfaces of Europa, Ganymede, or Callisto. Jupiter's moons are of intense interest to astrobiologists. Europa in particular, with its subsurface ocean beneath an icy crust, is considered one of the most likely places in the solar system to harbor life. If an alien civilization wanted to investigate the potential for life in our system, Europa would be high on the list. A probe sent to Europa could be looking for the same thing we are evidence of biology: microbes in the ocean, chemical signatures of metabolism. If such life exists, if 3I Atlas detects it, what happens next? Does it report back to whoever sent it? Does it collect samples? Does it interfere with the ecosystem, introducing contamination or altering the environment? We do not know the intentions. That is the central problem. An advanced civilization capable of sending probes across interstellar distances has goals we can barely imagine. They might be scientists, explorers, seeking knowledge for its own sake. They might be resource gatherers, cataloging planets and moons for future exploitation. They might be exterminators, eliminating potential competitors before they become a threat. The dark forest hypothesis suggests the latter. In a universe where civilizations compete for survival, revealing your location or capabilities is dangerous. If 3I Atlas is a probe from such a civilization, its mission might be reconnaissance followed by neutralization. Observe, assess, and if necessary, eliminate. That sounds like science fiction. It sounds paranoid, but history shows that when technologically superior civilizations encounter less advanced ones, the outcomes are often tragic for the less advanced. We have no reason to assume that pattern will not hold at the interstellar scale. Loeb does not claim to know what 3I Atlas is, or what its purpose might be. He simply argues that we should not dismiss the possibility of technology without thoroughly investigating. And the October 29th perihelion passage is the key moment. If the object is going to reveal its nature, if it is going to do something that cannot be explained as natural comet behavior, that is when it will happen. The challenge is that we will not see it happen. We will be blind during the critical period. All we can do is wait for it to re-emerge in late November and early December, recalculate its trajectory, and look for deviations. If it followed the predicted path, if it shows no signs of maneuvering, then maybe the technological hypothesis weakens. But if it is not where it should be, if the orbit has changed in ways that require thrust, then we have our answer, and then the real questions begin. Questions about what we do, questions about whether we try to communicate or prepare for defense, questions about whether humanity can unite in the face of an external threat, or whether we fracture into competing factions arguing about how to respond. Questions we have never had to seriously confront, because until now, the possibility of alien visitors was theoretical. 3I Atlas makes it real. In less than a month, we will know more. We will have data from the Mars flyby. We will see how the object behaves as it approaches the Sunday. And then, after it disappears behind the solar disk, we wait. We watch. We hope that when it re-emerges, it is still just a comet. But we prepare for the possibility that it is not. Chapter 7. The conspiracy theories exploding right now. When something mysterious happens, when official explanations feel incomplete, the internet fills the vacuum with speculation. 3I Atlas has become a lightning rod for conspiracy theories, and in the past 48 hours the chatter has intensified. Forums, social media, YouTube channels, everyone has a theory about what is really going on. Some of these theories are harmless speculation, people wondering, asking questions, connecting dots that might not actually connect. But some theories have gained traction, spreading through communities that already distrust official narratives, and a few of those theories touch on something uncomfortable, the possibility that information is being withheld, that we are not being told the full story, that there are things happening behind closed doors that the public does not know about. Let me walk through what people are saying, Not because I endorse these theories, but because they reveal something about how we process uncertainty and threat. The slowing down theory. In the last 72 hours, claims have appeared on Reddit and other platforms suggesting that 3I Atlas is decelerating, that its velocity relative to the Sun is decreasing in ways that cannot be explained by gravity alone. If true, this would be huge. Natural objects do not slow down unless they are thrusting against their direction of travel. A comet can speed up slightly due to outgassing jets, but slowing down requires firing engines backward, which comets do not do. The problem is that the claims are not well sourced. People cite vague references to observations or leaked data without providing specifics. When you try to track down the original source, it evaporates. That does not mean the claims are false, but it does mean they are unverified, and unverified claims in a high-stakes situation are dangerous, because they can cause panic or misdirect attention. What we do know is that Loeb's paper analyzed the trajectory through September 23rd and found no measurable non-gravitational acceleration. If 3I Atlas was slowing down, it would show up in the orbital data as a deviation from the predicted path. As of late September, no such deviation was detected. That does not rule out a more recent maneuver, but it suggests that if deceleration is happening, it started after the data cutoff. Then, there is the pulse theory. Some people claim that 3I Atlas is emitting regular pulses of energy every 17 minutes. 17-minute intervals allegedly detected by radio telescopes or other instruments, though again, no official confirmation has been published. 17 minutes is oddly specific. It is not a round number. It does not correspond to any obvious natural period, like a rotation rate or orbital resonance. If the pulses are real, they would be hard to explain naturally. Pulsars emit regular pulses, but pulsars are neutron stars, and their periods are measured in milliseconds to seconds, not minutes. 17-minute pulses from a small object would require some kind of active process, a mechanism that turns on and off with precise regularity. That could be artificial, a beacon perhaps, a signal indicator, the object's positional status, or maybe a data transmission, packets of information being sent at regular intervals. But we have to be careful. Radio astronomy is hard. Interference from human sources, satellites, ground-based transmitters, can create false signals that look like they are coming from space. Distinguishing real extraterrestrial signals from terrestrial noise requires rigorous analysis. The WOW signal was remarkable because it passed all the tests. It had the right characteristics, the right duration, the right frequency. The 17-minute pulses, if they exist, need to be verified by multiple independent observatories before we take them seriously. Another theory circulating is about transparency. Why is there so little information being released about 3I Atlas? NASA and other space agencies have been relatively quiet. There are official statements, basic facts about the orbit and composition, but not much detail. Some people interpret this silence as suspicious, as if information is being deliberately withheld to prevent panic. The counterargument is straightforward. Scientists are cautious. They do not rush to publish results before the data is thoroughly analyzed. Peer review takes time. Telescopes and spacecraft collect data. The data is downloaded, processed, checked for errors, analyzed, written up in papers, submitted to journals, reviewed by other scientists, and finally published. This process can take weeks or months. The October 3rd Mars observations just happened. The data is probably still being processed. We should not expect instant results. But the perception of secrecy fuels speculation. And in an age where information spreads instantly on social media, where people expect real-time updates, the traditional pace of scientific publication feels slow. It feels like hiding. Then, there is the NASA Juno question. Why has NASA not committed to redirecting Juno to intercept 3I Atlas in March? The maneuver is feasible. Juno is near the end of its mission anyway. The scientific payoff of a close encounter with an interstellar object could be enormous. So why the hesitation? Some suggest bureaucracy. NASA is a large organization with committees and approval processes. Changing a mission plan, even for a spacecraft nearing end of life, requires sign-offs from multiple levels. It takes time. Others suggest budget concerns. Redirecting Juno costs money, and if the encounter produces nothing interesting, someone will have to justify the expense. But a darker interpretation, popular in conspiracy circles, is that NASA does not want Juno to get close, that they know something about 3I Atlas that makes a close encounter risky or undesirable. Maybe they fear contamination, the probe being exposed to unknown biological or chemical hazards. Maybe they fear the probe being damaged or destroyed by the object if it is hostile. Or maybe they fear what Juno might discover information that would be difficult to keep quiet. I want to be clear, there is no evidence that NASA is hiding anything. The simpler explanation, that they are being cautious and following standard procedures, is far more likely. But the perception matters. When people feel they are not being told the truth, they fill in the gaps with their own narratives. And some of those narratives are unnerving. There is also chatter about the Epstein files distraction theory. Some people believe the announcement of 3I Atlas and the media attention around it was deliberately timed to distract from other news. Political scandals, economic troubles, whatever people are worried about, they suspect that a convenient alien scare is being used to manipulate public attention. Loeb addressed this directly in one of his blog posts. He pointed out that 3I Atlas is a real object, observable with the naked eye through a decent telescope. It is not a fabrication. It exists in space, moves at measurable velocity, and can be independently verified. It is not something he or anyone else can fake with a Jewish space laser or any other nonsense. The object is real. The trajectory is real. The anomalies are real. Whether those anomalies indicate alien technology is a scientific question, not a political one. But conspiracy theories thrive on distrust, and distrust is abundant. People who do not trust governments, who do not trust scientists, who have been lied to before, will not suddenly start trusting official statements about an interstellar object. They will assume deception, assume hidden agendas, assume the worst. The government hoax theory takes it further. A small but vocal group claims that 3I Atlas is not real at all, that it is a fabricated story, a psyop designed to prepare the public for a fake alien invasion, or to justify increased government surveillance and control. Project Bluebeam, an old conspiracy theory about holographic alien invasions, has been resurrected and applied to 3I Atlas. This theory is easy to debunk. Multiple independent observatories around the world have detected and tracked 3I Atlas. Amateur astronomers have imaged it. If it were fake, you would need a global conspiracy involving thousands of scientists and institutions across dozens of countries. That level of coordination is implausible. Occam's razor says the simpler explanation that the object is real is correct. But for people already inclined to distrust, no amount of evidence will suffice. They will claim the images are doctored, the data fabricated, the scientists complicit. Once you go down that rabbit hole, there is no coming back with logic. Another theme is psychological preparation. The idea that 3I Atlas, regardless of whether it is alien technology, is being used to acclimate the public to the possibility of extraterrestrial life. Disclosure by degrees. First we find exoplanets, then we detect biosignatures in the atmospheres of those planets. Then an interstellar object shows up with anomalous properties. Each step primes us for the next, building towards an eventual revelation that we are not alone. Some people welcome this. They see it as a positive, an expansion of human understanding, a step toward joining a galactic community. Others fear it. They worry about the implications, the disruptions to religion and philosophy, the potential threats from advanced civilizations. And hovering over all of this is a simple question. If 95% of the world population does not know 3I Atlas exists, is that because the information is not being disseminated, or because most people do not pay attention to astronomy news? Probably the latter. Space news, unless it involves dramatic images or immediate threats, does not capture mainstream attention. An interstellar object with anomalies is fascinating to people who follow space science, but to the general public, it is abstract. That could change fast if something dramatic happens. If 3I Atlas maneuvers, if probes are detected, if there is any confirmed evidence of technology, then it will be front-page news everywhere, and then the conspiracy theories will explode exponentially, because suddenly the stakes are real, and everyone will want answers. Chapter 8. Scientists at War. The Academic Bloodbath. Science is supposed to be objective, dispassionate, follow the data wherever it leads, test hypotheses rigorously, accept results whether they confirm or contradict your expectations. That is the ideal. But science is done by humans, and humans have egos, reputations, careers. When someone challenges the consensus, when someone proposes ideas that threaten established thinking, the response can be brutal. Avi Loeb has experienced this firsthand. He is not the first scientist to be ostracized for unconventional ideas, and he will not be the last. But the intensity of the backlash against him, particularly regarding Oumuamua and now 3I Atlas, reveals something uncomfortable about how the scientific community handles anomalies that do not fit neatly into existing frameworks. Let me start with NASA's response. Tom Statler, NASA's lead scientist for solar system small bodies, was asked about the claims that 3I Atlas might be alien technology. His response was dismissive. He told reporters that 3I Atlas looks like a comet, does comet things, and very strongly resembles comets we know. He acknowledged it has some interesting properties that differ from solar system comets, but concluded that the evidence overwhelmingly points to it being a natural body. That sounds reasonable on the surface. Most anomalous objects turn out to be natural once we study them in detail. Extraordinary claims require extraordinary evidence, and so far the evidence for 3I Atlas being artificial is circumstantial. But notice what Statler did not address. He did not explain the nickel without iron. He did not explain the trajectory alignment and timing coincidences. He did not explain the mass problem or the anti-tail. He simply said it looks like a comet and left it at that. This is a pattern. When scientists want to dismiss an idea without engaging with the specifics, they fall back on generalities. It looks normal. It behaves as expected. The alternative explanation is too wild. But if you actually examine the data, the details do not support the simple comet narrative. The details are weird, and weird deserves explanation, not hand-waving. Jason Wright, an astronomer at Penn State University, has been more direct in his criticism of Loeb. Wright runs a blog called Astro Wright, where he discusses astronomical topics and occasionally critiques papers he finds problematic. He wrote multiple posts dissecting Loeb's arguments about 3I Atlas, and his tone was scathing. In one post, Wright accused Loeb of dismissing evidence that contradicted his hypothesis. Specifically, Wright pointed out that Hubble images clearly show a coma around 3I Atlas, a fuzzy cloud of gas and dust, typical of comets. Loeb acknowledged the coma, but argued that the distribution was unusual, with more brightness in front than behind. Wright called this dismissal of the coma a smearing and much stupider take than simply ignoring the images. Wright also criticized Loeb for continuing to push the alien hypothesis even after spectroscopic data from Webb and the very dot. Large telescopes showed that 3I Atlas is outgassing molecules like carbon dioxide, water, and cyanide. To Wright, the presence of these molecules confirms it is a comet. Why would an alien spacecraft vent water and carbon dioxide? The simplest explanation is that it is ice sublimating, not propulsion. Loeb's counter-argument is that the chemical composition is anomalous. 95% carbon dioxide is not normal. Nickel without iron is not normal. Just because the object is shedding volatiles does not mean it is a natural comet. It could be a spacecraft with a surface layer of accumulated ice and dust from its interstellar journey. When that surface heats up, it outgasses, mimicking cometary activity, while hiding the technological core beneath. Wright finds this unconvincing. In his view, Loeb is stacking speculative assumptions to preserve a hypothesis that should be abandoned. Wright wrote that Loeb's behavior reminds him of conspiracy theorists who demand others prove them wrong, rather than providing positive evidence for their claims. The burden of proof, Wright argues, is on Loeb to show that 3I Atlas is artificial, not on everyone else to prove it is natural. Steve Desch, a planetary scientist, went even further. He reviewed one of Loeb's papers and called it sloppy work beneath the level of an undergraduate. Desch literally graded the paper as if it were a student assignment and gave it a failing score. He criticized the methodology, the assumptions, the conclusions. He accused Loeb of cherry-picking data and ignoring alternative explanations. This is not normal academic discourse. Peer review can be harsh, but publicly mocking a colleague's work, comparing it to undergraduate mistakes, crosses a line. It signals not just disagreement but contempt, and it raises the question of why the reaction is so intense. If Loeb's ideas are obviously wrong, why not just ignore them? Why go out of your way to publicly humiliate him? One answer is that Loeb's ideas are getting attention. Media outlets cover his statements. The public finds the alien hypothesis exciting, and when the public gets excited about ideas that mainstream scientists consider fringe, those scientists feel they have a responsibility to push back, to correct the record, to prevent misinformation from spreading. But there is another dynamic at play. Loeb is a prominent figure. He has credentials that cannot be easily dismissed. He is a Harvard professor, former chair of the astronomy department, widely published, highly cited. He is not a crank operating on the margins. He is establishment, or at least he was. And when someone with that level of credibility starts making claims that challenge the consensus, it threatens the gatekeeping function that academia relies on. Science advances when new ideas are tested and either validated or refuted, but there is also a conservative force in science, a resistance to ideas that are too far outside the mainstream. This resistance serves a purpose. It filters out noise, prevents every wild speculation from consuming resources and attention, but it can also stifle innovation, delay paradigm shifts, and punish scientists who take risks. Loeb's papers on 3I Atlas have faced unusual obstacles. One paper he co-authored with Eric Keto, which provided a physical explanation for the anti-tail observed in Hubble images, was declined by a journal editor who stated that the results would be of rather limited interest to the research community as a whole. That is a polite way of saying, we do not want to publish this. Another paper, the one on the lack of non-gravitational acceleration implying an anomalously massive object, was blocked by Army moderators for several days without explanation. Arxiv is a preprint server where scientists upload papers before peer review. It is not supposed to be a gatekeeping mechanism. Papers are posted quickly with minimal editorial oversight. But in this case, the paper was held up, and when it was finally released, it came with no explanation for the delay. These incidents might be coincidences, or they might reflect a coordinated effort to slow the dissemination of Loeb's ideas, to give mainstream scientists time to prepare counter-arguments, to control the narrative before it gets out of hand. Loeb himself has addressed the criticism directly. He argues that science should be about curiosity and open-mindedness, not about enforcing orthodoxy. He points out that anomalies are how we learn. If we dismiss every anomaly as noise or error, we miss opportunities to discover something new. The history of science is filled with examples of ideas that were ridiculed at first and later proven correct: continental drift, the Big Bang, black holes all faced intense skepticism before the evidence became overwhelming. Loeb also notes that his critics often do not engage with the specifics of his arguments. They say it is a comet without explaining the nickel. They say the trajectory is random without addressing the probability calculations. They say he is speculating without acknowledging that his speculations are grounded in data and physics, and there is a personal dimension to this. Some of Loeb's critics have made negative remarks about him as a person, not just his ideas. They have questioned his motivations, suggested he is seeking publicity, accused him of harming science by giving credibility to fringe theories. An editor handling one of his papers went public with negative personal comments, and when Loeb complained, the editor's boss defended the behavior as not unethical. This is academia eating its own. When a field feels threatened by unconventional ideas, the response can be vicious. Careers are built on reputations, and reputations are fragile. If you are known as the person who endorsed a crazy idea that turned out to be wrong, that stain does not wash off easily. So scientists protect themselves by distancing from anything that smells risky, and they attack those who do not play it safe. But what if Loeb is right? What if 3I Atlas is artificial, and the scientific community dismissed the evidence because it was too uncomfortable, too disruptive, too far outside the Overton window of acceptable ideas? The cost of that mistake would be enormous. We would have missed a chance to prepare, to study, to understand what we are dealing with, and future historians would look back and ask how we could have been so blind. Chapter 9. What if we're wrong? The natural explanation attempt. Let me be fair to the skeptics. Let me present the strongest case for 3I Atlas being a natural object, because that is still the most likely explanation. Extraordinary claims require extraordinary evidence, and while the anomalies are intriguing, they do not yet rise to the level of proof. Science demands that we consider all possibilities, and the natural explanation deserves a thorough hearing. Start with the chemical composition. 95% carbon dioxide, 5% water. Yes, that is unusual for a comet, but unusual is not impossible. Comets form in different regions of protoplanetary disks, at different temperatures and pressures. The ratio of volatiles depends on where and when the comet formed. A comet that formed farther from its parent star, in a colder region where carbon dioxide ice is more stable than water ice, could have a carbon dioxide as rich composition. The cosmic ray cooking hypothesis also has merit. 3I Atlas has been traveling through interstellar space for potentially billions of years. Cosmic rays are relentless. They bombard any surface exposed to space, breaking chemical bonds, creating new molecules, altering the composition. Water ice exposed to cosmic rays can be converted into carbon dioxide and other compounds through radiolysis. Over millions of years, the surface layer could become heavily processed, carbon dioxide dominated, while the interior remains water-rich. The fact that the carbon dioxide production is increasing as the comet approaches the Sun could simply mean that deeper layers are being exposed as the surface ablates, or that subsurface pockets of carbon dioxide ice are being heated and venting through cracks in the crust. Comets are not uniform objects. They have layers, pockets, variations in composition, outgassing that can be complex and time-dependent. The nickel without iron is harder to explain naturally, but not impossible. The Very Large Telescope team suggested nickel carbonyl as a possible source. Nickel carbonyl is a molecule formed when nickel reacts with carbon monoxide. It is extremely volatile, sublimating at very low temperatures. If 3I Atlas contains nickel carbonyl, perhaps formed through exotic chemistry in its parent system or during its journey through space, that would explain why nickel is detected without iron. Iron might be present, but locked in less volatile compounds, oxides, sulfides, silicates, materials that require higher temperatures to break down. If the current temperature is high enough to vaporize nickel carbonyl but not high enough to release iron, you would see nickel emission without iron emission. As the comet gets closer to the Sun and heats up, iron might eventually appear in the spectrum. The trajectory alignment with the ecliptic plane, 1 in 500 odds, sounds improbable, but with a large enough sample, improbable things happen. If we observe hundreds or thousands of interstellar objects over the coming decades, we should expect to see a few that align by chance. 3I Atlas might be that 1 in 500 case. The timing that brings it close to Mars, Venus, and Jupiter, 1 in 20,000 odds, is harder to dismiss. But again, With enough objects, rare configurations will occur, and there may be selection effects we are not accounting for. Maybe objects that align with the ecliptic and pass near planets are simply more likely to be detected because they reflect more sunlight. Detection bias could skew the statistics. The mass problem, the fact that 3I Atlas is much larger than the previous two interstellar objects, could reflect population diversity. Maybe small interstellar objects like Oumuamua and Borisov are common, while large ones like 3I Atlas are rare. With only 3 detected, the sample is too small to judge distributions. Perhaps we just got lucky or unlucky to find a large one so soon. The anti-tail, the forward glow, can also be explained by asymmetric outgassing from a non-spinning nucleus. If the nucleus is tidally locked or rotating slowly, and if most of the outgassing happens on the sunward side, you get a plume expanding forward, scattering sunlight, creating the observed brightness. The lack of a prominent tail might simply mean dust production is lower than expected, or that the grains are large and less affected by radiation pressure, so they do not form a long trail. Every anomaly has a potential natural explanation. They might require rare conditions, exotic chemistry, or statistical flukes, but they are not impossible. And when faced with 2 hypotheses, one requiring known physics under unusual circumstances, and one requiring alien technology, Occam's razor tells us to prefer the simpler explanation. The simpler explanation is that 3I Atlas is a comet, an unusual comet, yes, an ancient comet from a different part of the galaxy with chemistry and behavior we have not seen before, but still a comet. A natural object shaped by billions of years of cosmic evolution, not an artificial construct. This is the position most astronomers take, and it is reasonable. It acknowledges anomalies while maintaining that extraordinary claims need extraordinary proof, and the proof, so far, is not there. We have circumstantial evidence, patterns, coincidences, but no smoking gun, no definitive signs of artificial structure, propulsion, or communication. The observations scheduled for late October and November will provide more data. The higher-rise images from Mars, the spectra from Earth and orbiters, the monitoring as the object passes perihelion and re-emerges each dataset will either strengthen or weaken the natural hypothesis. If the data fit the comet model, if the object behaves predictably, if there are no further anomalies, then the technological hypothesis fades. But if new anomalies emerge, if the object does something comets do not do, then we must reconsider. And that is all Avi Loeb is asking for, not that we accept his hypothesis as proven, but that we keep an open mind and follow the evidence. There is a middle ground between assuming every anomaly is aliens and assuming no anomaly could ever be aliens. That middle ground is careful investigation without prejudice. It is saying we do not know, and we are going to find out. It is recognizing that the universe is full of surprises, and sometimes those surprises challenge our understanding in profound ways. One argument I find compelling is about age. If 3I Atlas originated from the thick disk of the Milky Way, as its velocity and trajectory suggest, it could be 7 to 11 billion years old, older than the Sun, older than Earth, older than any object in our solar system, except perhaps a few primordial asteroids. An object that old has witnessed the evolution of the galaxy. It has seen stars born and die. It has passed through regions of intense radiation, dense molecular clouds, perhaps close encounters with other stars. Over such immense time, it has been shaped by processes we can barely imagine. Its surface bombarded, eroded, altered, its interior transformed by chemistry and physics we do not yet understand. When you are dealing with something that ancient, you cannot assume it will behave like the comets in our solar system, mere infants at 4.5 billion years old. The chemistry could be different, the structure different, everything could be different in ways we have not anticipated. So maybe the anomalies are not signs of technology. Maybe they are signs of extreme age and exotic origins. Maybe 3I Atlas is teaching us that the universe is more diverse than our models account for, that natural processes can produce outcomes we did not predict. Maybe the lesson here is humility, an acknowledgement that our understanding of comets and interstellar objects is still in its infancy. That would be a valuable lesson. It would expand our knowledge, make us better scientists, and it would not require rewriting our worldview or confronting the possibility that we are being watched by intelligences far older and more advanced than ourselves. Chapter 10. Humanity's Crossroads. What happens next? We are approaching a moment of clarity. In the coming weeks, multiple spacecraft will observe 3I Atlas with unprecedented detail. The Mars flyby on October 3rd will give us our first resolved images. The perihelion passage on October 29th will test whether the object behaves as a natural comet or does something unexpected. The re-emergence in late November and December will reveal whether its trajectory has changed. Each observation is a test, and each test will either confirm or challenge what we think we know. Between November 2nd and November 25th, ESA's Jupiter Icy Moons Explorer spacecraft, called JUICE, will observe 3I Atlas using multiple instruments. JUICE is currently on its way to Jupiter after a flyby of Earth and Venus for gravity assists. It is in a perfect position to view 3I Atlas during one of its most active phases, shortly after perihelion, when the comet should be at peak brightness and outgassing rate. JUICE carries cameras, spectrometers, and a particle detector. The cameras will capture images of the coma and any tail that develops. The spectrometers will analyze the composition of the gas and dust, looking for molecules that might have been missed in earlier observations. The particle detector can measure ions and charged particles in the vicinity of the comet, providing information about how the solar wind interacts with the outgassing material. ESA says JUICE will likely have the best view of 3I Atlas in a very active state, because JUICE is looking at the comet after perihelion. When it has been maximally heated by the sun, the activity should be intense. If there is ever a time when 3I Atlas will reveal its nature, this is it. Active comets shed their surface layers rapidly, exposing fresh material underneath. Any hidden structures, any technological components, would become more visible as the disguising layers of ice and dust ablate away. The data from JUICE will not be available immediately. ESA notes that JUICE is currently on the far side of the Sun from Earth, using its high-gain antenna as a heat shield. It is communicating through a smaller medium-gain antenna at reduced data rates. The full dataset from the November observations might not be downlinked and processed until February 2026. That is months away, but when it arrives, it could be definitive. There is also coordination being considered between JUICE and NASA's Europa Clipper mission. Both spacecraft carry ultraviolet spectrographs, instruments that can detect atoms and molecules by their ultraviolet emission. If both spacecraft observe 3I Atlas simultaneously from different positions, they can triangulate the distribution of gases in the coma, building a three-dimensional map of the outgassing. That level of detail has never been achieved for an interstellar object. Now let me address the question everyone is thinking. Should we attempt to communicate with 3I Atlas? Should we send a signal, a message, trying to make contact if it is indeed artificial? Avi Loeb has written about this dilemma. He points out that there are two main risks to sending a message. First, we do not know the capabilities or intentions of whatever might be listening. If 3I Atlas is a probe from an advanced civilization, that civilization might perceive an unsolicited message as a threat. In the dark forest framework, revealing yourself is dangerous. Broadcasting a signal saying, "Here we are, we're intelligent, we exist," might be interpreted as a challenge or a declaration of hostility. The response could be violent. Second, even if the intentions are not hostile, communication might be misinterpreted. Our message might convey something we did not intend. Language, even mathematical or pictorial language, is rooted in context and assumptions. An alien intelligence with a completely different evolutionary history, different sensory modalities, different cognitive structures, might misunderstand what we're trying to say. A friendly greeting might be read as an insult, An offer of cooperation might be seen as submission. On the other hand, if 3I Atlas is a probe specifically sent to detect intelligent life, it might be waiting for us to respond. The wow signal, if it really came from 3I Atlas, could have been an invitation, a test to see if anyone is listening. By not responding, we might be missing an opportunity for contact, for learning, for accessing knowledge far beyond our current understanding. Loeb suggests that before we send any message, we should observe, treat it like a blind date. Watch the other party. Try to understand their behavior, their characteristics, their intentions before starting a conversation. If 3I Atlas maneuvers in ways that suggest intelligence, if it shows signs of being responsive to observation, if it does anything that indicates awareness of us, then we can consider communication. But rushing to send a message without understanding what we're dealing with is reckless. The Arecibo message, sent in 1974 toward the globular cluster Messier 13, was a low-risk communication. The cluster is 22,000 light-years away. Even if someone receives the message and responds, the round-trip time is 44,000 years. We are in no danger from a civilization that far away, at least not on human timescales. But 3I Atlas is here. It is in our solar system. If it can receive and respond, the response could come within months. That changes the risk calculation entirely. We have to think carefully about what we do and what the consequences might be. There is another scenario to consider. What if we are not the first? What if 3I Atlas has been communicating with something else in the solar system? What if there are other probes, older arrivals that we have not detected, and they are coordinating? The wow signal might have been directed not at Earth, but at another receiver elsewhere in the solar system. We might have intercepted a transmission never meant for us, like overhearing a conversation in a language we barely understand. If that is true, then the question is not whether to communicate, but whether to reveal that we intercepted the message. And maybe the smart play is to stay quiet, to listen, to learn what we can without announcing our presence. The Galileo project will be monitoring the skies after October 29th. Loeb has stated that the project will check for increased activity of unidentified anomalous phenomena following the perihelion passage. If 3I Atlas is a mothership releasing probes, those probes might become visible as they enter Earth's atmosphere or maneuver in near-Earth space. The Galileo observatories are specifically designed to detect and track such objects. Detection alone would be historic. Confirming the existence of alien technology in our solar system would be the most important discovery in human history. It would answer the question of whether we're alone. It would prove that intelligent life exists elsewhere, that it is capable of interstellar travel, that it's interested in our solar system for reasons we can only guess at. But detection is just the beginning. After detection comes the question of response. Do we try to intercept? Do we attempt communication? Do we prepare defenses? Do we alert the public or keep it classified? These are decisions that no one person or even one government can make. They require international coordination input from scientists, ethicists, military strategists, philosophers, representatives of all humanity. The problem is that we do not have such a framework in place. There is no international body with the authority to decide how humanity responds to alien contact. The United Nations has a committee on the peaceful uses of outer space, but it is focused on treaties about satellites and space stations, not protocols for encountering extraterrestrial intelligence. SETI, the Search for Extraterrestrial Intelligence, has proposed guidelines for what to do if we detect a signal from space, but those guidelines assume detection via a radio telescope, not a physical object in our solar system. We are unprepared, and that unpreparedness means that if something happens, the response will be chaotic, fragmented, reactive, rather than planned. Different countries will pursue different strategies. Some will want to communicate, some will want to hide, some will want to attack. The result could be confusion, missed opportunities, or escalation of tensions that we cannot afford. Loeb argues that we need an organization, an international body tasked with monitoring interstellar objects and developing response protocols. The organization would assess each object on the Loeb scale, determining the level of concern and the appropriate response. Objects ranked low on the scale, clearly natural, require no special action beyond scientific observation. Objects ranked high, confirmed technological with potential threat, require coordinated response including possible interception, communication, or defensive measures. The Vera C. Rubin Observatory, scheduled to begin full operation soon, will discover interstellar objects at an unprecedented rate. Currently, we find maybe one every few years. With Rubin, we will find dozens per year, possibly hundreds. Each one will need to be assessed. Each one could be the visitor that changes everything. Having a framework in place before the next discovery is critical. Think about what the next few months could bring. If 3I Atlas is natural, we will have learned about ancient comets from other star systems, expanded our understanding of planetary system formation and evolution, and refined our detection methods for future visitors. That alone is valuable. If 3I Atlas is technological, we will have confirmed that we are not alone, that advanced civilizations exist, that they are exploring the galaxy, and that they have reached our solar system. That knowledge would reshape every aspect of human civilization. Religion, philosophy, politics, science, all transformed by the realization that we share the universe with others. The stakes could not be higher, and the clock is running. So here we are, September turning to October, watching the sky, waiting for answers that might arrive in days or weeks or months. 3I Atlas continues its journey inward, carrying with it questions we've never had to seriously confront. Is it a messenger from another world? Is it a scout? Is it simply an ancient wanderer, a frozen relic teaching us that the universe is stranger than we imagined? The beautiful thing about this moment, the thing that makes it bearable despite the uncertainty, is that we get to witness it together. Every telescope pointed at that moving point of light, every scientist analyzing the data, every person listening to this and wondering what it means. We're all part of the same story, a story about curiosity, about reaching beyond what we know, about being brave enough to ask questions even when the answers might terrify us. I think about Jerry Eman in 1977 staring at that printout, seeing those numbers that should not have been there, writing "wow" in red pen because what else could he say? He did not know what he had found. 48 years later, we might finally understand. That signal might not have been a mystery without an answer. It might have been a greeting, a hand extended across the darkness, from something that was already on its way. Whether 3I Atlas is a comet or a craft, whether it brings knowledge or danger or simply passes through and leaves us wondering, it has already given us something valuable. It has reminded us how small we are, how new we are, how much we do not know. It has reminded us that the universe does not care about our assumptions, our models, our comfortable certainties. It simply is. Vast and strange and full of things we've barely begun to comprehend. The next few weeks will bring data, images from Mars, observations as the object reaches the sun, and then the waiting as it disappears behind the solar disk, and we hold our breath, hoping it re-emerges where we expect, behaving as we predict, or hoping, perhaps, that it does not, that it reveals itself, that it confirms we are not alone. Either way, we will never stop watching and learning. That pursuit of understanding despite fear and uncertainty, that is what makes us human. That is what drives us to build telescopes, to send spacecraft across the solar system, to stay up late analyzing data, to ask the questions that have no easy answers. Thank you for spending these hours with me, diving into this mystery, sitting with the discomfort of not knowing. If you found value in this exploration, if it made you think or wonder or see the night sky differently, I would be grateful if you would like this video and subscribe. It helps more people find these stories, and right now, this story matters. This story might be the most important one any of us ever hear. Before I let you go, the standard reminder: Everything shared here is based on published scientific papers, official observations, and public statements. I've presented multiple perspectives, from those who see evidence of technology to those who argue for natural explanations. The purpose is not to convince you of one answer, but to show you the questions, to give you the information to think for yourself. I'm not claiming to know what 3I Atlas is, no one does. We're all waiting for the same answers. The universe is full of mysteries. Some of them are beautiful, some are terrifying. Some, like 3I Atlas, might be both. As October unfolds and the data arrives, as we watch and wait and wonder, remember that we are witnessing something rare, a moment when the veil might lift, a moment when everything could change. Keep looking up, stay curious, and wherever you are, whatever time it is as you listen to this, know that somewhere above you, moving through the darkness at 60 kilometers per second, an object from another star is approaching its rendezvous with our Sunday. What happens next? We will discover together. Good night.